Megan Becker.
Who do I mute?
I have. Okay, it's asking me to leave the meeting. Okay. Yeah. Thank you. It's a pleasure for me to introduce Professor Megan Becker, who will be giving a seminar for us this afternoon, morning, or evening, depending on where you are in the globe. I have worked with Megan for many years. Megan joined UCT around about 2006 after completing a degree in geology. And then she pursued her master's, which had a blend of geology and the processing, and went on to do a PhD at Pretoria University. She's been working as a researcher in the Department of Chemical Engineering at UCT, from researcher, senior researcher, associate professor, and now professor in the department. She takes leadership in the area of mineralogy and has authored a few books in process mineralogy, which have been read by many people. And we thought, as communicators, I think we should be aware of what is happening in terms of process mineralogy and be integrated with the measurements that are done in there for us to make headways in what we are trying to do in the area of minimizing energy, as well as delivering particles that can be recovered downstream. So today it's a pleasure to listen to Megan, who will give us insights in the area of liberation and process mineralogy in general. Thank you.
Thank you, Aubrey. Good afternoon, good morning, good evening, all. And thank you for having me to present today. So what I would plan to present is really about mineral liberation. And I was going to start off just re-emphasizing why it's important, but also then just going back to some of the basics, defining what it is and how do we measure it. And also then focusing on how do we trust the data that we get. There's so many devices and so many platforms and so many people can give you liberation data, but how do you know you can trust it? And if you can't trust it, then you can make some potentially not so great inferences and conclusions. So, and then I'm going to end with a case study just showcasing how we use some of this data in a slightly unusual application. So liberation obviously has to do with the release of your valuable minerals, and the picture on the right is from Esch's, one of Esch's drawings that is about liberation. All right, so let's just recap. In terms of mineral processing, I know you really like, communicators like to break rocks, but let's not forget that the aim is actually to liberate the valuable minerals. Then we can separate them for further recovery. And when I first came across this acronym, it was LSD, dispose. And actually now we see so much the situation has changed. Now it's about reuse, recycle, repurpose, do something with the waste. So let's just illustrate the relationship between texture and plant design. And this came from a paper from Norm Lotter a number of years ago. And it was an example of a nickel copper sulfide deposit. And here, what's nice about this figure, they show you the relationship between different textures. So these are obviously different false color images of different tiles from a machine like QuemScan. And what you're seeing here, the red is pentlandite, the yellow is chalcopyrite, and the orange is bornite. This is a very coarse texture. That scale bar is about 3.5 millimeters. And so in the circuit that they set up here, they started with having a very coarse primary grind, followed by some sort of flash float to recover what we call the massive sulfide textures. Then they grind a bit finer, and that would then go into something more like the net textured. So here you're looking at the orange and yellow little blebs, and obviously they're all connected, but the grains could be fairly fine. And then there's a regrind to sub 38 microns, and here you're going for these tiny little yellow and orange specks, and I would call that a disseminated texture. So there's a massive sulfide, net textured, and disseminated, and 3 different textures from this ore body, and each of them has its own grind requirements, and then they float, just aiming to recover that material. So let's start. What is texture? So I've defined it as the interrelationship between the minerals of which the rock is made of. And from this, we'll get something like the grain size distribution. We know that for any mineral, it's not just one grain size, it's a distribution. This will help us decide what should be the target grind for liberation. But it will also determine, once we've broken up this rock, how many of these particles are liberated, and the ones that are not liberated, what are they associated with? Because it obviously depends on how they occurred in the rock before we broke it. It will then also define the particle properties. To a certain degree, we know that the machines also define that, and the type of breakage defines the particle properties. But for some rocks, and something like the case study I'll show you later with, which is based on chromite. Chromite as a mineral tends to have like these like golf balls, and it's got a very sugary type of texture. And when it breaks, it just keeps making more little golf balls. And so that is a function actually of the inherent texture. And then also it's going to determine the quantity of fine particles in addition to the breakage mechanisms. If you have minerals that are naturally very fine-grained, that's also going to play a role. So what textures do we see? So I think this is actually after Gowden, who geologists like to use textural terms that are very qualitative. So we use words to describe textures. So we could use things like I already mentioned earlier, something like disseminated. Can you see my mouse moving?
Yes.
Okay, so you can see something like disseminated, and the nice illustration I use for disseminated is like if you imagine some pepper and you grind pepper over your food, that pepper is now essentially maybe your valuable mineral. We've also got coated textures where we have naturally occurring rimming, and we can see this in many forms of alteration, especially supergene alteration. So if you have something like primary chalcopyrite and secondary chalcocite, you could see this type of texture. We can get these like lamellar textures where they're almost like these different lathes that are next to each other, simple binary particles, and then some of these very complicated textures. And because rocks are heterogeneous, you normally get a variety of these textures coming into your feed. So why is liberation important? And it also depends on what we're preparing it for. So in this example, we have a valuable particle 50% and gangue is 50%. The gray is 50-50. And this is a simple binary texture. This is a coated or rim texture, and this is disseminated. If I'm preparing it for something like flotation, that particle, the chances are it will be recovered. If it's a rim texture, so over here, your bubble will never see this dark phase, and so it's unlikely to be recovered. And the same here, not likely to be recovered. If you're going for something like density, then the particle texture doesn't really make a difference. It's about the absolute mass of that particle. Then over here, depending on how the density cut point is set, this is likely to be recovered, that will be recovered, and that texture will be recovered. And again, if you're preparing your material for leaching, this texture, your lixiviant should be able to see it. That one, your lixiviant has no access to the valuable unless you've used some form of grinding where you've created cracks. So potentially some sort of compression grinding that you've created a crack network that your lixiviant could access the valuable. If that is the case, then that might be recovered. But as it stands, it's unlikely to be recovered, and that wouldn't be recovered. So it's actually very important for us to decide to understand the texture, because all these particles have the same liberation, but they will behave differently in different separation processes. So how do we decide how much liberation is enough? We have to remember that we have to start off with understanding what nature's given us. So what is the original texture of the rock and the valuable mineral? What process are we preparing it? And then obviously something like this, you really understand this dynamic. The finer you grind, the more expensive it is, but you can get more recovery. And that balance moves according to energy prices. And that also sometimes, if you grind too fine, you open Pandora's box and you get another whole set of problems coming. So it's not always just grind entirely to liberate everything, potentially the stage liberation, and understanding the interplay for the later processes. So my colleague and mentor, former colleague and mentor, Dee Bradshaw, when I first lectured some of this material with her, she used to call it the Goldilocks effect. So it was either it's not too hot, too cold, it's just right. So in this case, you don't want too much liberation, you don't want too little liberation, you've got to get it just right. So what would Goldilocks want? So let's just start with the definition. So Barbary wrote this very famous book on liberation, and his definition of liberation was a 3D fragment consisting, a particle is a three-dimensional fragment consisting of one or several mineral phases. Notice it's three-dimensional. A grain is a 3D entity consisting of only one mineral. So obviously a particle could have more than one mineral. Liberation is the state of a particle consisting of only one phase. And a composite locked particle obviously has more than one phase. And then the degree of liberation, by definition, is the fraction of the phase by volume present is liberated divided by the volume of the phase present in the population. So I know I'm going back to the basics, but a lot of people sometimes get this confused. A liberated particle, that is 100% liberated. It's 100% of mineral A. That mineral, now we're obviously only just looking at an area, two-dimensional area. 75% of that particle is the blue. It is 75% liberated. That's 50% liberated, 25% liberated, and we would call that particle barren. So for any individual particle, the liberation of that particle is the grade of the particle. But obviously, you have thousands and millions of particles in a stream. So when you take all the grades of all the individual particles and you composite, that's then where you get now we need to find the liberation of the stream. So how do we go about measuring liberation? So the workhorse still is using two-dimensional sections. So in the earliest measures of liberation, they would use something like optical microscopy, but they would take a particulate matter, prepare it into some sort of polished section, and then do some sort of point counting. Towards the 90s and the 2000s, and now pretty much standard, everyone is using some form of AutoSem EDS to measure liberation. We can also do it with volumes. So if we use something like X-ray computed tomography, and that obviously is a much better measure of liberation because we're measuring a three-dimensional entity, and liberation by definition is a volume-based measurement. One of the hindrances of the XCT for a number of years has been the discrimination between the different minerals, and we're seeing a lot more advances in that, and the processing software is also getting a lot more advanced. So I think that this is becoming a lot more common than it already is, and potentially one day this will overtake the AutoSem. Okay, the other point to mention on liberation, when I use liberation data, I always define the cut point. So if I'm doing something by area, I will always say greater than 80% is liberated, or the greater than 90, because liberation, sometimes we use different cut points for different commodities. And it also depends on actually the floatability of the different commodity. But that's why it's important we always define what we mean when we say liberated. Okay, so I just wanted to show you what some of the original liberation data look like. This would have come from optical microscopy. This comes from the 1980s, and they looked at chalcopyrite. And now, if the chalcopyrite wasn't liberated, they looked in terms of if it's a binary particles, what other mineral is it associated with? And if it didn't fall into that category, then it goes into a ternary particle. Obviously, this is done on a size-by-size basis. We get better quality data, more confidence in the data when you do it sized, but it also provides more information. Like then we know, okay, the coarse material is, sorry, the unliberated material sitting in these size fractions, those are the ones you need to grind fine or something like that. Then when the automated systems start coming in, because everything was digitized, we could now start working with different liberation classes. And this just uses cut points of 10%. So here's the liberation class, that's the cumulative mass. And over here, we go from 10 to 20. So any particle that plots there has less between 0 and 10% of that valuable mineral in the particle. If it's a particle plotting between in this less than 100, it's obviously got between 90 and 100% of that valuable mineral in the particle. And then you can plot this cumulative curve, and you can look at the trends between the different size fractions. So this is one of the ways people look at liberation data. Another way that's quite popular is to just group it a bit further using terminology like locked and middlings and liberated. And again, it's done on a size-by-size basis. And in this way, here you see most of the locked material sits in the plus 75 micron. Most of the liberated material sits sub 75 microns. I like to look at my particles, and that's because as a geologist, I was trained to look under a microscope, and a picture says 1,000 words. So I want to actually look at the characteristics of the particles. So this example, I'm looking at chalcopyrite liberation across a number of size fractions. And this category here, so I've written an algorithm that tells me which particles to put in this block. And then I've said, if it's not associated with if it's not liberated, I want to know the particles that associate with silicates, with sphalerite, with galena, with iron sulfides. So this is pyrite and pyrrhotite, and with magnetite. So now I can look at the characteristics of the particles, and I can understand what's happening in the system. I can then go and quantify that, and here then plot a graph showing chalcopyrite liberation and association done by different size fractions. It's also very important that I report the number of particles I've measured, because if you're looking at this data set and you see 10, 20, 30, 40, you might not have as much confidence, whereas if you're seeing particles in the hundreds and the thousands, you have more confidence in the data set that is more representative. One thing to just describe here, so when I report something like association, so to capture the liberated particles, I would have used a descriptor that says that the area in that particle is more than 90%. And then I want to understand of the material, all the particles that have less than 90% of chalcopyrite in them, what is the relationship of that particle to the mineral on the perimeter? So what minerals sit next to it? And then obviously that is quantified. And that's how I've got this association. So the liberation here is reporting something about an area measurement, and the association is telling me about the perimeter characteristics of the particle. Okay. In the 90s, McIver and Finch came up with this concept called the mineral liberation, or the mineralogically limited, or the theoretical grade recovery curve. And it's a very useful thing to use because it explains the potential of the material. And people tend to forget sometimes that it's actually defining the opportunity that you have. So in order to construct this curve, I will go and do measurements of the entire stream, and I will map every single particle, or how many particles in the stream, and then I'm going to start ranking the particles in terms of the quality of the particle, and obviously the amount of each particle type. Then plot this curve, and I find the window, what is the operating curve. So let's go, it's rather easier to show by a graph. So I've got on the right, and the Y, I've got cumulative mineral grade, and the X, I've got cumulative mineral recovery. My first data point, it's obviously a dummy data point up at 0% recovery. I will recover only the fully liberated material. So the dark is the valuable mineral, and that will get me to point A, and the grade at point A is going to be 100% because I'm only recovering fully liberated particles. Then I start recovering what I would call high-grade middlings. So now I can accumulate the recovery of the fully liberated material, the high-grade middlings, and it gets me to 50-something% recovery. And obviously, we recalculate the grade, and it's coming down. We do this again with the low-grade material, low-grade middlings, and then the locked material. And so we then plot this curve. obviously, once you've recovered all the valuable mineral, anything further progressively that you would recover would get you to F, which essentially is the feed grade. So what happens if you plot this curve with plant data? So say you look at a concentrator and the star is the point where the concentrator is operating. We know that according to that theoretical grade recovery curve, the opportunity for grade improvement is this, and the opportunity for recovery improvement is that. Or I can sort of go to, diagonally to the right, and I can get a bit more grade and recovery. I know, though, that it's impossible to get anything into this area. So if I was doing a reagent trial or something, I cannot get a grade recovery in this dark gray area. It's impossible. The only place you can improve is up to that curve. The only way to get beyond the curve is to move the curve. And you move the curve by grinding finer, or by introducing, obviously, if your classification grinding circuit is linked and there's recycle streams, by changing the classification, because then obviously you're changing what materials being milled where. And in that way, you can move this theoretical grade recovery curve. So it's a wonderful curve. It defines the potential, and I'm not always sure that it actually gets fully appreciated and used to the value that it can deliver. So that's, now I've just covered what is liberation, how do we measure it? But now we have to understand some of the weaknesses of the data and how do we know to trust it? So in practice, because we're using things like CREM scans, MLAs, and TEMAs, we are measuring liberation in terms of an area measurement, whereas liberation is based on a volume-based measurement. So we are taking a two-dimensional estimate of a three-dimensional three-dimensional measurement of feature, and then inferring. And when we estimate a higher dimensional information from a lower dimensional property of measurement, we have this thing called stereological error. And what we see is in practice, these 2D measurements overestimate the parameter. So if one looked at this binary particle, 50-50, and you imagined any number of different, if this was a sphere, you could have any number of different intersections. You could have intersections like this one, the black one. So if we say the black is the valuable, that is fully liberated. That's very close to fully liberated, high-grade middling, whereas those white particles I would think are actually barren. This one I would call the black material locked, and this one I would call it a middling's roughly half-half. So you can have any number of intersections, and that will cause the stereological error. And what we find is that these two-dimensional measurements overestimate the parameter. So this, again, is the theoretical grade recovery curve. This comes from a study that Jan Miller had done on a phosphate ore. And he measured the theoretical grade recovery curve with tomography-based measurement. So the red is a 3D volume-based measurement, and the blue is a two-dimensional measurement, area-based measurement from something like an MLA, CREM scan, TEMA. So you can see that the area measurement is suggesting the material's finer, and actually the actual performance of this concentrator sat exactly on the curve. So in the case here, there was no further room for improvement for that concentrator. And if there had been after the blue, they might have been trying to reach to something that was unobtainable. From a grain size distribution, the 2D shown in blue tends to estimate that it's slightly finer. And so we know this error exists. What do we do about it? We sort of just work around it. And I think that if the mineralogy says a grinding target must be this number, there's always some sort of window that's provided on that estimate to account for the stereological error. And then the other thing to just remember that it's the simple textures that have the worst bias. So this texture here of a simple binary, the magnitude of the bias is the most. Whereas this texture here with the black, any intersection, so we look where the red line's going, I'm pretty much still going to get the same answer. And if it's fully liberated, whatever the red intersection through the particles, I still get the same answer. It's these simple textures that are introduce the most bias. So what do we do with this? I know that there were a number of studies that went in the last 20 years looking at stereological correction factors. They tend not to be used, even though we can apply it. People tend to just prefer to report the actual measurement, appreciating the stereological error. We also work with sized samples, and that also helps us sort of minimize some of the error too. And maybe if I just show you this quickly, if I used a size sample and I virtually remove all these tiny particles here, I'm also, which could be like the apex of the egg, essentially removing particles that are not giving a good representation of what that should be. Okay, so if you take a sample, you do your mill feed, mill product, and you want some liberation data. Let's first understand about where the error can come in. So the biggest error probably is actually the sampling, and I've seen numbers up to potentially 60% error related to sampling. We need to get representative samples, and in a sense, for those of us doing the mineralogical measurements, we're trusting that whoever sampled the circuit or the drill core, they are giving us samples that are representative. We then need to know that when the sample comes into a lab, that the sample receipt, that protocol of the custody of the sample, there's no error for confusion or contamination or anything like that. Then we need to have confidence in how the sample's been prepared to measure the liberation, and then there's actually the confidence in the measurement. So what is the confidence in the measurement? This comes from something like how many particles have we analyzed, and then the other part is how accurate is the measurement. And the only way we can get confidence is that would be then looking at other techniques, validating between different techniques. So how do we reduce error from sample prep? Obviously, I'm not going into sampling error. That's a whole nother book of its own. We use things like representative subsampling, rifflers, micro rifflers, and we work with narrow size fractions. We are also very specific in terms of how we mount material, and you probably have heard of this thing called vertical sections or transverse sections. If we have material that is dual density, we run the risk of the coarser material or the heavier particles settling through the resin, because obviously we put the particles in a resin and let it cure, settling in the particles, in the block that we've made as that resin cures. And so in the study, what they did, they made a block, then they cut it in half, and they turned it on the side, and they looked at the mass of the individual particles. Obviously, they estimated the mass knowing the density and the area of the particle. So over here, this is the surface, which everything would have settled. And remember, there's two sides. So that particle there is 4-point-something grams, 6 grams, or something like there is 0 grams and 0.0-something grams. If I were to analyze only that surface, I would get results that were very wrong and completely overestimate the abundance of the heavier material. If I analyze only here, I will completely underestimate the mineralogy. The point is to get this representative cross-section. So if I'm mapping this material and that material with my AutoSem EDS, I'm going to get a good representation. I also need to know that however the samples have been prepared for this automated SEM device, that I've got a very good quality polish. Some minerals, one specific example being something like chromite, they can potentially pluck. And if they'll pluck out, then you're again not presenting a representative sample to the machine. And then obviously any number of forms of post-analysis processing. So something like here, you've got 2 particles, pink, and this big one here. You can see that that is just stuck to the side of it. It's not a primary texture. And again, that one's sitting there. So we have measures that we use in sample prep to try and minimize this effect, but we also use something like post-analysis processing, and we tell the software virtually separate those. So make that into 2 particles. And if we do any liberation or association or any form of textural measurement on something like this, chances are we're going to get the data wrong. Okay, Then what is the confidence in the measured mineral grades? So there's this formula, it's actually a very old formula from the 1960s, and it can be used to estimate the confidence. So there was a chart that went with this original paper, and if I just show you the example here, on the red dot, P is the real content of the mineral, percent by volume. So in this example, we're suggesting it's 10%, and we have counted 900 points. Because it then sits on this chart on 2%, we know that for the 900 points that we've counted, the real value, this is 2 sigma, is anywhere between 8 and 12%. And some of the software actually gives you this this error measurement in when they report it from the actual AutoSem EDS device. So obviously, the more observations, the more confidence we have in terms of that we've estimated the mineral content correctly. Then I just wanted to show you, so this came from a paper where they looked at drill core and they used bootstrap resampling, trying to understand confidence intervals. So here is, so the MLA, they obviously mapped the whole section they were interested in. They then back calculated a copper grade because they know which copper minerals were there and how much of each copper mineral is there. They back calculated a copper grade and then they assayed a copper grade. And we plot these parity charts. And here is the one-to-one line, and obviously you want everything to sit on that line. So for something like copper, where we're dealing with absolute numbers like 0.2 to 0.6%, you can see the error bars are quite small. Here they did gold, and now we're gone into ppm, and you see the size of the error bars. And that's got to do with the fact that because gold is a precious commodity, there's just so much less of it. So for us to get more confidence, we have to analyze so much more material to get confidence in that measurement. And so this is why something like analyzing concentrates, we can get really good confidence in the measured grades, but give us a tails, well, we struggle to find particles. And the confidence in the data is obviously less because we've measured less particles. There has also been a measurement that was a method that came out in the 1990s to look at confidence in liberation data. And this is based on what they call the cumulative liberation yield, which is basically an inverted way of showing the liberation distribution that I showed you earlier. And so they got cumulative liberation yield versus liberation class. So we did this comes from a master's student of mine, and she was looking at acid rock drainage testing. And the standard for acid rock drainage testing is -6 millimeter material. So she obviously sized it into a number of size fractions, and we measured the particle properties in each of the size fractions. And so for the material that is sub 150, that's shown in black, the error bars in the confidence limits on this are very small. The plus 150, they're getting a little bit bigger, but if you look at the plus 2 millimeter material, big error bars. And that's obviously because we have to present so many more particles, it takes so much longer for us to analyze it because we're mapping so much more particles, or we need to. And so it's easy for us to have confidence in liberation data on fine material, but the coarse of the material, it's again a problem in terms of analyzing sufficient particles because they're so coarse and they take so much machine turn. Then we have this thing about how accurate is the measurement. So what is standard practice? For many, and not necessarily all, but I will do this all the time on any mineralogy data we report, we will take the mineralogy that we get, the mineral grades, we apply a mineral composition, and we back calculate an element composition, element concentration. We then measure this with some other assay technique, XRF, ICP-OES, and we plot this parity chart. Over here, I've shown the 10% line, so 10% above and 10% below. And obviously, an ideal, if we say we're going to work in a 10% bounds, is that we want all the back calculated numbers to sit within a 10% window. If I have any issues with sample prep, I might see something like iron. So if I had to see the gray dots belonging to iron plotting out here, so I'm overestimating the iron, then I know that I potentially have had settling in my samples. And sometimes I have to, we juggle things like iron and magnesium. If the one's high and the other's low, we know that because many silicate minerals they can take different ratios of those elements into the same mineral. We just have to tweak the compositions that we're using to back calculate this number, and then we can pull it to the line. So that's one method, but that just gives me confidence that I've calculated the right compositions. But it doesn't tell me that I've got the right minerals, because I can have more than one mineral that has a similar composition. So then I will go to something like quantitative X-ray diffraction. And this is another method that allows me to measure mineral grades. I might not do this on every single size sample, but I will do this again. So the QEM scan gives me a mineral grade, the XRD gives me a mineral grade, and I plot this on a line. And again, I want it to sit within the 10% bounds. One of the issues with XRD, if anyone's worked with it, is because the way we work out quantitative mineral grades using this thing called Rietveld refinement, it normalizes it. So everything must add up to 100. So if one mineral is out, every mineral is out. And I also know that the detection limit is about 2 to 3% for something like XRD. So anything with, I would say, less than 5%, I might not get a very accurate number. But if I know that the XRD says it's there and the AutoSEM says it's there, but they're low concentrations and my assays match, then I've got the confidence. So I will use both sets of measurements to give me confidence in the mineralogy data. Okay, so then I just want to show you about how bad it could get. So I've gone about how we have the confidence in the data, but this was a very interesting paper that I took part in. It was in 2014, 2015, and the paper came out in 2016. And this Canadian group from CanMet, they prepared representative aliquots of a copper concentrate from Sudbury, and they sent it to whoever was interested. And they asked us to analyze the mineral grades and the chalcopyrite liberation. And they only gave us 10 grams, and they said, prepare the material however you want, whatever your standard method. And so every subsample was given a unique code, and everyone who took part in this, it wasn't quite a round robin, then also indicated how they prepared the sections. So the majority of people prepared one block, some prepared more than one, and you'll see there any number of different types of methods that were used. Some are using these what we call transverse or vertical sections. Other people just use standard sections. So within every different lab, they all did it differently. So what happened with the results? So the material balance of chalcopyrite was about there, and here you see the variability came out. So essentially, every group was given the same sample or a representative sample of the same material, but the chalcopyrite grades could vary between up to 80% or 60% when it was around, there was obviously close to a 20% 10% above and 10% below what the groups came out with. Now, if any group had been using your back calculated copper grades, you would have spotted if this was your measurement up here, or that was your measurement down there, that you were either overestimating or underestimating copper. Then they wanted people to look at liberation. And the majority of people, this is cumulative liberation yield again. So here are the liberation classes. That's the cumulative chalcopyrite yield. Most of the groups were sitting over here, but there are definitely a few outliers. So in this case, the people said there was this 354 pink group said there was a lot more unliberated material than there was. And same for 222, where most people are saying actually is mostly liberated, which considering it's a chalcopyrite concentrate, one would expect the liberation to be quite high. So this is just an idea of some of the variability that the measurements can have. If we are very cognizant of all the steps that I've talked about, knowing about potential for errors in sampling, sample preparation, measurement, and we do things like these back calculated things, we are able to develop more confidence in those measurements. And then when we hand them over to you to do your comminution test work and your modeling, you're going to have more confidence that those numbers are meaningful. Okay, so the final thing, I just wanted to give you an application of liberation data, and I chose a slightly unusual case study. I've done lots of studies on textual measurements that we've published, but they actually weren't all liberation. So I went back quite far to a paper that was published in 2008, and this was actually the work that was done on Aubrey's own PhD on the 3-product cyclone. And Malcolm was also one of the co-authors of this paper. So let's just give a bit of context to the UG2. So the UG2, it's a chromatite rock ore in South Africa. And in it, the 3 dominant minerals is chromite between 40 to 60%, depending on the mining cut, and then pyroxene and plagioclase. And I've given you the densities. You can see chromite's close to 5, pyroxene and plagioclase more likely 3. So we already see this is a dual density ore, and it's going to have potential problems for classification. In this platinum group element ore, the PGM, obviously the grades are a few grams per ton, but the grain sizes are generally all less than 10 microns. And these PGMs are associated, some of them are associated with sulfides, and some of them are locked in silicates. So in a conventional circuit, when you have something like the dual density ore, what happens is when it goes through the cyclone, the fine chromite potentially can get sent for regrind, and it just gets ground finer and finer and finer, and you get this high circulating load. And the coarse silicate material, which potentially has locked PGM, is sent directly to the float, and those PGMs are lost. And so we land up with a high circulating load. We introduce a lot of fine chromite into the float circuit. And because there is so much chromite in that ore, I said 40 to 60%, if that chromite is recovered by entrainment, that's a lot of chromite that's been recovered. And we find that the concentrate, the Cr2O3 quality of that concentrate can be too high. And if you then pass it on to the smelter, they then get uptight because that chromite doesn't do good stuff in the smelter. And so they will penalize them for if it's something like toll smelting. So any UG2 circuit is always trying to reduce the chromite Cr2O3 content in their final concentrate. And so Aubrey's PhD used something like the 3-product cyclone as a methodology to overcome these issues. So just a quick schematic, that's obviously your standard cyclone, and then this is the 3-product cyclone. So you have 2 overflows, and in the configuration that we worked on in this paper, the outer overflow caught that fine chromite and the coarse silicate material, whereas the inner flow went directly to the float. This outer flow then went on a screen, and the screen undersize, which was the fine chromite, would have gone straight to the float. Screen oversize, which would be the coarse silicates, potentially with locked PGMs, went back to the mill for grinding. And then what we went and did, we worked out the theoretical grade recovery curve. So this looks a little bit different to the ones I showed you before, because the grade is a bit harder to estimate. And when we do anything on PGM analyses, the PGM mineralogy, there's more than 200 different PGM minerals. Knowing the exact density of any individual PGM mineral, especially when they intergrown with one another and so have so much compositional variation, is quite difficult. So we can't measure an absolute grade, but we can rank them in terms of a grade. And so we took the conventional cyclone, that what basically was the overflow was the float feed, and we took the 3-product cyclone, what was then the new float feed, and we looked at the PGM mineralogy. And so for the conventional, the PGMs were only 21% liberated. For the 3-product cyclone, it was 34% liberated. And you will see, so the dotted line is the conventional, and then well, obviously the black, which is the 3 product, takes the whole difference. We will see that this theoretical grade recovery curve, it's pushed higher towards the right-hand corner, suggesting that we've got a better quality feed that's going in. So this was an example where we showed that you can move the theoretical grade recovery curve just by using the 3 product cyclone. But obviously we know because it was linked to a screen and the screen oversize was then sent back to the mill, we were changing the liberation properties of that feed. And so that was a nice case study, and it probably was the first study when Aubrey and I officially worked together. Okay, and that's about it from me. So I just wanted to show you, go back some of the basics. What is liberation? How do we measure it? But how also do we trust the data and know that what you're working with is representative of the material and it's a reliable measurement? So thank you.
Thank you very much, Megan, for that thought-provoking presentation, and very interesting indeed. We have time for questions. Those with burning questions, please, the floor is open.
Hi, Megan. Klaas from Osenko.
Hi.
Very interesting. I was a little bit late to the party, so I may have missed this, but I'm quite interested in your thoughts on, so the standard practice is, let's say we have a sample, we size it into 3 fractions, you analyze the fractions individually. My experience is that how those are recomposited once you've got the analyses on the 3 individual fractions done, how that is recomposited back into a single sample. I think there's a lot of potential source for error there, especially as size is obviously very closely linked to liberation. Very interested in your thoughts on that.
Yeah, I guess there's 2 philosophies. You just weight it back according to the particle size distributions. The other one, you weight it back according to particle size distributions and how much material of the valuable mineral is in the stream. I've done both methods, and generally the results are pretty similar.
Okay.
Does that answer your question?
Yeah.
Maybe it also depends on the type of stream.
Yeah, probably.
And the properties of that stream, but I've compared them, and I generally I haven't seen too much difference.
Okay. Okay. No, that's good. That's good to know.
Thanks, class. Any other questions?
I always have questions, Megan. I'll ask the reverse question because I found this an interesting area in terms of progressive upgrade. Do you get asked to measure the liberation of the gang?
Oh, yes.
You know, because we always talk about liberation of the mineral, but the majority of it's gang. So progressive upgrade, if you can measure liberation of gang and figure out when you should be removing it from the process. I just wondered if you'd been dealing with that.
So I guess the work that we've done more on understanding gang liberation is linked to, so again, the platinum industry. So these ores have a lot of pyroxene, orthopyroxene, which is a magnesium silicate, and under potentially weathering and hydrothermal conditions, some of this orthopyroxene forms talc. Talc is a hydrous magnesium silicate, and it is naturally floatable. And so we then looked at understanding talc liberation in quite a bit of detail on different ores. And what we have actually shown and published and written up is that sometimes if you just simply measure the grade of talc in the feed, it doesn't tell you about how much naturally floating gang there is, because the naturally floating gang is the composite particle of talc and orthopyroxene. It's not only liberated talc. So if you have an orthopyroxene particle with a sniff of talc on it, it will float unless you're using a depressant. And so understanding the amount of naturally floating gang between different ores, we've actually found that you can't simply just say there's 3% talc in this ore, there's 5% talc in that ore, therefore the one with 5% talc will have more naturally floating gang. one actually has to understand the talc grain size distribution. And the more disseminated the talc, the finer, more disseminated, the more naturally floating gang. So obviously when you then look at mass pull, you'll see that relationship coming out. So yeah, that's one example where we looked at gang liberation. The other one is actually doing in a project now. It's about pyrite rejection and understanding why pyrite's getting into a conch when it's supposed to be being rejected, and what is it about the pyrite. So in that case, it's sulfide gang as opposed to non-sulfide gang.
Yeah, in a way, you want the other way around. You don't want any contamination of your gang with value.
Yes.
Yeah. Any other questions? We still have time.
Yeah, I've got a question. It's Megan. Megan, it's Grant from Azenco as well.
Grant.
I was the one that kept class late to this meeting, so sorry about that, class. So I arrived a little bit as well. But one of the things, I mean, I've seen lots of technologies, comminution technologies that start out talking about liberation, improvements like HPGRs and Vera liberators, looking at as they initially started talking about liberation improvements, but quickly they were kind of pushed to the side. I guess my current mental model, and I'd love to hear your interpretation of this, but at very, very low rates of compression, there's some stuff done in the US where they looked at like millimeters per day. They got improved liberation. And at very, very high rates of compression, like above 300 meters per second, kind of really, really fast gas gun results, there was improved liberation. But in between that, I think there hasn't been much that's actually shown that mechanical breakage can improve liberation. So the only work I've seen improved liberation is really about the classification, and the 3 product cyclones, one, the screens another. Do you have any comment on that? Is there, in your view, have you seen any results that show that mechanical breakage can improve liberation in readable strain rates, or whatever you want to call it? Or yeah.
So I'm thinking of a PhD student that Aubrey and I shared with Jochen Peterson a few years ago, and this was a leaching study, and he looked at high pressure grinding rolls, and obviously then he used a 3-dimensional method like tomography, and he looked at the crack network. And so because you're inducing the cracks, these are potentially ways that the lixiviant could access the valuable mineral. And so in that context, he got better results. Yeah. For PGMs, it's very hard to interpret, probably because, well, we measure so few PGMs, but also, so I mean, you can see there was 100 measured there. That's nowhere near my thousands that I mentioned earlier. If I have a PGM that is attached to a sulfide mineral, the sulfide mineral is likely coarser, and or say the PGM is locked in a sulfide or attached to the sulfide. The sulfide's probably coarser, and depending on the species of the PGM, the sulfide may also be more floatable. So if I then go and break the PGM from the sulfide, I actually reduce the probability of the PGM being recovered in flotation, because if it stays with the sulfide, it's more likely to be recovered on the virtue of the sulfide floatability. So the PGM data is a lot more difficult to understand and interpret, because it's not only liberation, because I don't want to ruin the association of the sulfide to the PGM, because that helps me with recovering those PGMs.
Okay, thank you.
Marcelo?
Okay, thanks, Avi. A great lecture there, Megan. Excellent for communities to be on the same page as you mineralogists, quantitative mineralogists. My question is really on the borders of what you presented, which is being somebody who has been involved so much with measurement of liberation. I was wondering what your feeling is about what we call the holy grail in the comminution era, which is to be able to predict liberation from models. Of course, you mentioned Godin's work, and then since the 1930s until last year, a couple of years ago, people have been doing this, of course, being able to look at the unbroken rock texture and be able to predict. And I was wondering your feeling about this. How mature or how far are we from being able to do that, given the appreciation that you have for really having good measurements? So in that case, good predictions will be important as well.
I think the most progress that I've seen that's the most promising is Marco Hilden's work. I'm sure we can do it at some point. We just really have to understand the dynamics between because no rock breaks entirely randomly. Every rock has some component of non-random breakage that's because of the texture. And so when we get our head around that, yeah. But I think Marco Hilden's models, he's done some really good stuff in this space, and I'm sure you know the model.
Okay, excellent. Thanks.
We have a few minutes for one or two quick questions. Okay, yeah, Andre.
Yeah, sorry, I didn't put up my hand. Thank you, Megan, and yeah, very interesting. And I think for me, the one comment about the gang liberation, yeah, that's something that we are very keen. We are busy looking into. We've discovered things like pyrite with a little bit of carbon, or graffiti carbon on the surface.
It will float.
And we sometimes, yeah, we don't know, or even carbon with silicates. That we don't fully understand yet, but that's definitely something of interest to us. And then the other thing, just in general, what I often have debates with Lucy is about liberation class. I said, how do you choose? So we use, I think, Charles can correct me, I think anything more than 90% exposed surface is considered as liberated, fully liberated, but not. I just want to this quiet, but not clear, because it's I've asked, is there not like a standard definition for? I think it's probably where your liberation curve can be of quite value, but yeah, it's clearly not something that's almost like site specific.
So I know Bill Johnson had done some work. So you can define liberation how you want, but should the definition of liberation be based on what is recoverable? So if a particle contains 70 potential pyrite, and I know he's used this example, that particle will float. So is it liberated?
Yes.
So should the definition of liberation, the cut point, be based on that which you know will be recovered or not?
I can see you as Lucy's teacher, because that's what she told me as well. So it probably makes sense, especially now that you've confirmed it. It does make it depends. Yeah, that makes sense. I guess I should go with that.
Which is why I just said explain. Always the actual cut point must be defined, because people out of different applications and different personal preferences will use different cut points. And I use different cut points between precious minerals and base minerals. So yeah, we just have to always specify what it is, so the person who's reading that report knows what you mean.
Yeah, I think that's probably the important bit, just to specify, and maybe why you've used those specifications.
Thank you very much. Let's thank Megan for a very good presentation and good discussion at the end of the presentation. Thank you very much, Megan. We really appreciate your
thank you all.
your being here. So for the there will be another seminar, GCC seminar, at the end of April. Please support the seminar. We are still looking at what the waste topic will be at that time, and you'll be informed in due course. Thank you very much, Megan, and thank you to all of you for supporting this. We had a very good attendance today, which we like seeing all the time when we have these seminars. The purpose of the seminars is to share knowledge, and it's one of the good platforms where we can engage and learn and also participate and impart whatever we know. Thank you very much.
Thanks, everyone. Thanks again.
Bye.
Yes.
Bye, everyone.
Yeah.